In the deep dark, 12 billion years away, James Webb caught something curving through space that should not exist yet. A chain of 20 massive galaxies, bowed like a cosmic spine, stretching 13 million light-years across the void. And inside it, two giants already gone quiet burned through, ancient, impossible for their age. You're about to travel into a structure that breaks the rules of how the universe was supposed to grow. A hidden river of gas, a ghost twin called the leaf, a dark scaffold pulling it all together. If wonders like this pull you in, hit subscribe, take a breath. We're going in. It started as a smudge, just a faint, curving smear of light across a portion of sky most astronomers had already looked at 100 times before. The team running the data wasn't even hunting for a giant structure. They were combing through deep infrared images, pulling out the oldest, faintest galaxies they could find. Background work, the kind of careful, slow scanning that usually turns up nothing dramatic. Then someone noticed the shape. It wasn't scattered. It wasn't random. The galaxies in this slice of the image were lined up, beaded together along a soft, sweeping curve, almost like a vine bending through dark water. One galaxy here, another a little farther along the same arc, then another and another. 20 of them, at least, all leaning into the same shape. That shouldn't happen by accident. Galaxies in the early universe were supposed to be sprinkled across the void like loose grains of sand, random, lonely, slowly drifting toward each other over billions of years. What the team was staring at looked organized, as if something invisible had already drawn them into formation long before they had any right to be drawn anywhere at all. The astronomer running the analysis went back and checked the image again, then ran it through different filters, then pulled the raw data fresh from the archive to make sure nothing in the processing pipeline was tricking the eye. The curve was still there. The galaxies were still beaded along it. Real, confirmed. That was the first surprise. The second one came when they zoomed in on individual members of this strange chain and started pulling stellar properties from the light. Two of the brightest galaxies in the structure were enormous, heavy, compact, dense at the core. The kind of galaxies you would expect to find in the modern, mature universe. Not floating inside a cosmic structure that, judging by its light, had to be ancient. How ancient was the next thing they had to figure out? To answer that, they needed something called redshift. It is a measurement astronomers use the way a forensic scientist uses a fingerprint. Light from a distant galaxy gets stretched as it travels across an expanding universe. The farther it has come, the more stretched it gets. The more stretched the light, the older the source. The team locked onto the galaxies in the chain, pulled their light apart into wavelengths, measured exactly how stretched it was, and then ran the numbers to figure out how long this light had been traveling before it hit Webb's mirrors. The answer would change what they thought the structure was. It would change what they thought it meant. It would change how they understood the early universe itself. Because if this curving chain of galaxies was as far away as the early signals were hinting, then it was not just unusual. It was something the standard model of cosmology said should not be possible. A structure too organized, too massive, too far back in time. A piece of the cosmic story that did not fit the chapter it was in. The team stared at their screen, waiting for the redshift number to settle. What it told them next sent the project into territory nobody on the team had been prepared for. The redshift came back at 3.44. For someone outside astronomy, that number means nothing. A small decimal, easy to skim past. But inside the room where the team was working, those 4 digits landed like a stone dropped into still water. 3.44 meant the light from this curving chain of galaxies had been traveling toward Earth for nearly 12 billion years. The Webb telescope was not seeing the structure as it exists right now. It was seeing it as it looked when the universe itself was only about 2 billion years old. A child, barely past its first growth spurt. That alone would have been a strong result, but the implication ran deeper. Because the chain was not just a few galaxies caught in a snapshot. It was a coordinated structure. 20 massive galaxies, gravitationally tied together, beaded along a curve more than 13 million light-years from end to end. To put that in human terms, our entire Milky Way is about 100,000 light-years across. The structure Webb had found, stretched roughly 130 Milky Ways laid end to end, and it had pulled itself into that shape only 2 billion years after the universe began. That is the part that froze the room. Standard cosmology has a clear story about how big structures form. Galaxies first. Small ones. Lonely ones. They drift, they merge, they slowly clump. Over billions of years, the clumps grow into groups. The groups grow into clusters. The clusters knit themselves into the gigantic web of filaments we see today. It takes time. A lot of time. The cosmic vine, as the team eventually nicknamed it, had no business being this organized this early. It was like finding a fully grown oak tree in a field that had only been planted last spring. Something had skipped ahead in the timeline, and the team had to be sure. So they did what good scientists always do when reality stops behaving. They ran the numbers again. They pulled spectra from individual galaxies. They confirmed that the redshift was the same across the entire chain, not just one or two members. The galaxies were genuinely sitting at the same cosmic distance, in the same cosmic moment, woven together in the same cosmic structure. There was no trick of perspective, no accidental alignment of foreground and background, no data error. The vine was real, it was huge, and it was old in a way the universe was not supposed to allow. A confirmed scientific result, with all the awkward consequences that came with it. The team began drafting their paper carefully. They knew what kind of attention this would attract. Anything that strains the standard model of cosmology gets pulled apart by the rest of the field within hours of going public. They wanted every data point locked down before they let go of it. But behind the careful writing, a quieter excitement was building, because they were also realizing something else. The vine was not alone in that patch of sky. There was a second pattern starting to emerge in the background, fainter, softer, bent at a different angle, almost as if a second structure was hovering behind the first, and nobody on the team was ready for what that turned out to be. Imagine a bow, not the kind you tie, the kind an archer pulls back, all curve and tension, drawn taut between two ends. Now stretch that bow across 13 million light-years of empty space. That is the shape Webb pulled out of the dark. The cosmic vine does not sit in space like a cluster or a clump. It bends, it arcs, it sweeps gracefully across one whole region of the sky, as if some invisible hand had drawn the galaxies along a single sweeping curve and then walked away. Most cosmic structures we know about are blobby. Galaxy clusters tend to look like swarms of bees, dense in the middle, fading toward the edges. Even the great filaments of the cosmic web are messy and tangled, more like roots than ribbons. The vine breaks that pattern. It is clean, long, surprisingly elegant. To picture the scale, hold this in your mind. Our Milky Way is about 100,000 light-years wide. The vine is 650,000 light-years wide along its short axis. Along its long axis, it stretches 130 Milky Ways laid end to end. That is one structure, one coordinated assembly of galaxies, curving across a stretch of cosmic distance so vast that light, the fastest thing we know about, would need 13 million years just to cross it from one tip to the other. And every galaxy along that curve is moving, not freely, not randomly. They are bound together by gravity, pulled gently toward common centers of mass that lie hidden along the spine of the vine itself. The team mapped the positions carefully. 4 subgroups emerged, like beads strung at intervals along the curve. Each subgroup is itself a small forming cluster, with its own dense knot of galaxies pulling on its neighbors. The subgroups are slowly creeping toward each other, dragged together by the gravity of the whole structure. Give it a few billion more years of cosmic evolution, and those 4 subgroups will collide, merge, compress into a single, monstrous galaxy cluster. The vine, in its present elegant bow shape, is a snapshot of that process caught roughly halfway through. Webb did not just photograph a structure, it photographed an event, a cluster being born, in slow motion, across millions of light-years of cosmic real estate. That is the part that turns the discovery into something stranger than a measurement. You are looking at a piece of the universe in the act of building itself. The kind of construction project that takes longer than every human civilization combined, captured in a single still frame, because the light needed 12 billion years to reach us. But here is the question that started keeping the team up at night. If the vine is this organized this early, what was holding it together back when it formed? Galaxies do not just curve themselves, they follow gravity. And gravity in the early universe was being shaped by something invisible, something massive, something the team could not see directly in any of Webb's images. To find it, they would have to stop looking at the galaxies themselves. They would have to start hunting the empty patches between them, the dark places where, by every reasonable estimate, something enormous should have been waiting. The cosmic vine was found in a very particular place, a long, narrow rectangle of sky between the constellations Ursa Major and Boötes. Astronomers call it the extended Groth strip. If you have never heard of it, you are in good company. To the unaided eye, the strip looks like absolutely nothing. No bright stars, no glowing nebulae, no famous landmarks. Just a thin sliver of dark between the Big Dipper and the Herdsman that you would walk past on any clear night without noticing. That emptiness is exactly why astronomers love it. A patch of sky with nothing in the foreground is a patch of sky you can use to look very, very far away. No bright nearby stars to drown out faint signals. No dense gas clouds to block the view. Just a clean window, opening directly onto the deep universe behind it. For decades, that window has been one of the most carefully studied scraps of sky in all of astronomy. The Hubble Space Telescope stared at it for hundreds of hours. So did big, ground-based telescopes. So did infrared instruments. By the time Webb arrived, the extended Groth strip had already been mapped, photographed, and re-photographed more times than almost any other patch of cosmos. Astronomers thought they knew what was in there. They were wrong. Webb came online with infrared eyes far more sensitive than anything that had pointed at the strip before, and when its first deep observations came back, the old map of that empty-looking sky began to fill in with things nobody had seen. Faint, ancient galaxies that previous telescopes had missed entirely. Tiny red points of light that turned out to be giants from the early universe, hidden behind dust and distance. Subtle structures, barely visible, that suddenly became obvious in the new wavelengths Webb could read. The extended Groth strip was not empty, it was just dim. And once Webb sharpened the picture, the dimness gave way to something almost embarrassing in its richness. The cosmic vine was buried in there, threading across the strip in a curve so faint that earlier telescopes had picked up bits and pieces of it without ever realizing the bits were connected. Webb pulled the connections into focus. It saw the same bow shape across multiple wavelengths. It tracked the redshift, galaxy by galaxy, until the chain became undeniable. This is one of the strangest lessons astronomers have to keep relearning. The places that look most empty are usually the ones hiding the biggest secrets. A truly empty patch of sky does not exist. Every dark window opens onto 12, 13, 14 billion years of cosmic history piled up behind each other. The extended Groth strip just happened to be the window where Webb caught a particular cosmic giant in the act of forming. And here is the unsettling part. The strip is one of many such windows. Astronomers have several other deep field regions they study with the same care. If a structure as huge and unexpected as the vine was hiding in this one, what is hiding in the others? The team had only just begun to grasp what they were looking at. The next step was to figure out how a curve of galaxies stretching 13 million light-years could possibly have formed so early, and the answer would lead them to an idea that astronomers have argued about for decades. A galaxy in a Webb image, at first glance, is just a blur of color, maybe a bright spot at the center, maybe a hint of structure around the edges, but mostly a soft fuzz of light. To turn that fuzz into a timestamp, astronomers use a tool called redshift. Here is the simplest way to picture it. Imagine standing on a sidewalk while an ambulance races past with its siren on. As it approaches, the siren sounds high. As it pulls away, the siren sounds lower. The pitch changes because the sound waves get stretched out as the ambulance speeds away from you. Light does the same thing. When a galaxy is moving away from us, the light it sends out gets stretched. The wavelengths grow longer. colors shift toward the red end of the rainbow. The faster the galaxy is fleeing, the redder it becomes. Astronomers call that color shift the redshift. In our expanding universe, almost every distant galaxy is fleeing from us. The space between us and them is literally growing, dragging them outward. The farther away a galaxy sits, the faster it appears to be moving, and the more its light gets stretched on the long trip toward Earth. That makes redshift a kind of cosmic ruler. Measure the stretch, calculate the speed, work out the distance. And because light takes time to travel, distance is also time. A galaxy 1 billion light years away is also 1 billion years in the past. For the cosmic vine, the team measured a redshift of about 3.44. That number translates into roughly 12 billion years of travel time. The light hitting Webb's mirrors today left those galaxies when the universe itself was about 2 billion years old. So when astronomers look at the vine, they are not looking at it as it currently exists. The galaxies in that chain may have changed enormously by now. Some may have merged, some may have died. The cluster they were forming may already be fully built, somewhere out there in the present-day universe, totally invisible to us, because the light from that current state will not reach Earth for billions more years. What Webb captured is the past, a frozen moment from the early universe, played back to us in slow motion. This is what makes Webb so unsettlingly powerful. Older telescopes saw the vine as a smear, if they saw it at all. They could not pull the redshift cleanly enough to know where in time the smear belonged. Webb cracked the time code. It pulled spectra from individual galaxies in the chain. It locked down the redshift for 136 confirmed members. It mapped the vine, not just in space, but in time, with surgical precision. And that precision exposed the real shock. If the vine is the size it is, and it formed when it formed, then the early universe must have been doing something far more aggressive than the textbooks suggested. Mass was clumping faster. Structures were rising sooner. The cosmos was not the slow, patient builder we had been taught to picture. Something was speeding the whole process up. Something was already pulling galaxies into formation by the time the universe was a quarter of its present age. And that something was about to come into focus. The first count was 20 galaxies, lined along the curve, each one heavy enough to qualify as a giant by any normal cosmic standard. That number, on its own, was already enough to make the discovery important. Then the team kept counting. Every additional pass through the data turned up more members. Faint galaxies that had blended into the background became, on closer inspection, full participants in the same structure. Dim red dots that nobody had connected to the vine turned out to share its redshift exactly. The chain grew. The 4 bright subgroups along the curve filled in with smaller companions, satellites, hangers-on. The head count kept climbing. By the time the most recent careful study finished its work, the confirmed membership had ballooned to 136 galaxies inside the vine itself, with another 47 attached to a faint background structure that the team would soon name the leaf. That is a lot of galaxies. But raw numbers do not capture what this means. To understand the weight of that count, picture our local cosmic neighborhood. The Milky Way and the Andromeda Galaxy are the 2 giants nearby, with maybe 50 smaller dwarf galaxies orbiting around them. That is our whole local group, about 50 members, dominated by 2 big players. Now picture a structure with more than 136 members already confirmed, not orbiting at quiet distances, pulled together along a single 13 million light-year curve with multiple subclusters, each one as packed as our local neighborhood and then some. This is not a forming local group. This is a forming galaxy cluster, the heaviest kind of cosmic city the universe ever builds. And it is being assembled in a region of cosmic time when, by every textbook, things this big should still be just diffuse clouds of gas, slowly collecting themselves. The team realized they were watching a process, not just looking at an object. The vine was not a static portrait. It was a slow-motion construction project, caught with its scaffolding still up and its workers still on the job. Some of those workers were doing dramatic things. Smaller galaxies along the chain were caught in mid-fall, dragged toward the dense central knots by gravity. Star-forming regions were lighting up as gas got compressed by the inrush. Some galaxies showed signs of recent collisions, their shapes warped, their light scrambled. The whole structure was busy with motion, even though every one of those motions had happened 12 billion years ago. And in the middle of all that activity, two galaxies stood out from everyone else. They were the largest, the most massive, the ones the team had first noticed, pulling their attention back to this patch of sky. Galaxy A and Galaxy E, sitting near the center of the bow, anchoring the whole formation. But while the rest of the Vine was active, busy, alive with star-forming chaos, those two giants were doing something nobody expected. They were quiet, not just less active, almost completely shut down. Their star formation had nearly stopped. Their light was old, settled, dominated by aging stellar populations that should not have existed yet at all. The team had to ask the obvious, awkward question. How did two galaxies inside the early universe already manage to grow old? Here is the picture cosmology has spent a century building. Right after the Big Bang, the universe was a smooth, hot soup, almost perfectly even. If you measured it from one side to the other, the density barely varied at all. Tiny ripples in that smoothness, ripples we can still see imprinted on the cosmic background radiation, were the seeds of everything that came later. Those seeds were small, so small that gravity needed billions of years to pull them into anything visible. The standard timeline runs like this. Gas clouds collapse first. Stars ignite inside the clouds. Stars cluster into the first small galaxies. Small galaxies merge into bigger galaxies. Bigger galaxies fall into groups. Groups feed into clusters. Clusters knit themselves into the cosmic web of filaments and walls and voids that carpets the universe today. Each step takes time. The biggest structures we see now needed almost the full age of the universe to assemble. Galaxy clusters in the present-day cosmos are the youngest, newest, most recently completed pieces of the whole construction project, which is exactly why the cosmic vine is a problem. The vine has the size, the membership count, and the gravitational organization of a forming galaxy cluster, the kind of structure that should still be sitting halfway built today. Yet Webb is showing it to us already taking shape 12 billion years ago, when the universe was only 2 billion years old. That is not a small wrinkle. That is a serious challenge to the timeline. If structures this large were already pulling themselves together that early, then mass in the early universe was clumping much faster than the standard model predicted. The seeds in the cosmic soup were either bigger than we thought, or gravity in the early cosmos was working harder than we knew, or some other invisible influence was speeding the whole assembly process along. None of those options is comfortable. Each one forces some part of the standard story to bend, and the vine is not a one-off oddity that astronomers can wave away. Webb has been turning up unusually large, unusually mature structures in the early universe at a rate that has the entire field reassessing assumptions. Massive galaxies that look too big too soon. Galaxy groups that look too organized too soon. Now an enormous bow-shaped chain that looks too coordinated too soon, with too many members already gathered together along it. A pattern is forming. The early universe was busier than we thought, building faster, assembling things on bigger scales than the textbooks allowed. Researchers are still arguing about what this means. Some think the standard model needs only a tweak, a small adjustment to how dark matter clumps in the early eras. Others suspect a deeper revision is coming. A few are quietly entertaining the idea that something fundamental about how mass behaves at cosmic scales might need to be rewritten. For now, the vine sits at the center of that argument. A piece of evidence too large to ignore, too organized to be a coincidence, too far back in time to fit the old story. Whatever was holding it together had been working long before Webb arrived to catch it in the act, and the next clue to what that was lay hidden in the spaces between the galaxies, in something the team could only see by what it was doing to the gas they could see. Galaxies are easy to picture. Bright, swirling pinwheels of stars. The kind of object that shows up beautifully in any deep image of the sky. But galaxies do not float in true emptiness. Around them, between them, woven through them, runs a much fainter substance. Hydrogen gas, cold, thin, almost invisible, but present everywhere along the great structures of the cosmic web. Inside the cosmic vine, that gas turned out to be doing something interesting. When the team mapped the gas distribution carefully, the bow shape did not stop at the galaxies. It continued. Smooth, faint streams of hydrogen connected one galaxy to the next, threading along the same curve. The vine was not a chain of separate islands. It was a chain of islands tied together by an underlying river. That river is the fuel supply. Galaxies cannot make stars without raw material. Gas falls into a galaxy, cools, collapses, ignites. New stars are born. The galaxy grows. The cycle continues for as long as fresh gas keeps arriving from outside. In the early universe, this resupply line was incredibly important. Galaxies were young, hungry, growing fast. They needed huge amounts of cold hydrogen pouring in along thin filaments of the cosmic web in order to build themselves up. The vine, with its rich gas thread, was perfectly positioned to feed every galaxy along its length. Some of the smaller galaxies in the chain showed exactly the signs you would expect from this kind of feeding. Bright knots of new star formation, compressed regions of gas glowing in the wavelengths Webb is built to read, young, hot stars lighting up the edges of the structure like sparks running along a fuse. This is one of the things that makes the vine a textbook example of how big cosmic structures grow. Not by sudden collisions, not by explosive events, by slow, patient accretion, gas flowing in, galaxies feeding, mass building up along a hidden filament until the whole structure has enough weight to start collapsing inward on itself. You can almost picture it as a river of nutrients carrying small fish from one place to the next, while bigger fish wait at the meeting points to feast. And there are meeting points along the vine, 4 of them, to be specific. The 4 subgroups the team identified are the dense knots, where the river slows and pools, where the gas piles up, where galaxies gather in higher numbers, where the building of the eventual cluster is happening most aggressively. The vine is a system, not a collection. A system with feeding lines, pooling zones, and central anchors. It behaves the way a small, early-stage version of a future galaxy cluster should behave. That is the elegant part. Here is the troubling part. For a feeding system this large to already be working, the underlying skeleton had to be in place even earlier. Gas does not flow into nothing. It flows along the contours of gravity. Something massive, invisible, and already organized had been shaping the cosmic plumbing here long before any of these galaxies even ignited their first stars. That something was not the gas itself. The gas was just being carried along. The real architect was hiding in the dark, pulling the strings, leaving fingerprints only in the way the visible matter arranged itself. And the team had a name for the hidden architect they were going to have to find. Numbers in cosmology can become slippery quickly. Once you start saying billions, the human brain tends to glaze over. So let us stay grounded. The cosmic vine, by the team's careful estimate, has a total mass of about 260 billion suns. Think of that as the gravitational weight of the entire structure, all galaxies and gas combined, expressed in units of one Sunday. 260 billion of those, pressed into a single coordinated shape, 12 billion years ago. For comparison, our own Milky Way weighs in at roughly 1 trillion solar masses if you include its dark matter halo. So, the vine, even at its early stage of assembly, is already in the ballpark of a quarter of the Milky Way's full present-day weight, all gathered into one organized formation. That is striking on its own. But here is the more important way to read the number. 260 billion solar masses is the early seed of something much heavier. Galaxy clusters in the modern universe routinely top out at hundreds of trillions of solar masses. A few of the heaviest ones reach into the quadrillion range. The vine is not finished. It is still pulling in more mass from the cosmic web around it. It is still merging its subgroups. It is still feeding off the gas filament running through it. Give it a few more billion years, and that 260 billion will multiply many times over. The vine is the down payment on a future cluster that will eventually weigh thousands of times more than it does now. What Webb caught is the early growth phase, the moment when the eventual giant was still small enough to be called a vine instead of a cluster. Mass estimates in cosmology are not guesses. The team did not pull 260 billion out of thin air. They measured the brightness of every confirmed galaxy. They worked out the mass of stars inside each one based on how that light was distributed across wavelengths. They included the gas they could detect along the filament. They added everything up with careful error bars and came out with their figure: confirmed mass, real number, solid measurement. And here is where the real tension begins. Because 260 billion solar masses of visible material is not enough to hold a structure of this size together by itself. Gravity is a tug-of-war between mass and motion. The bigger the structure, the more mass you need at the center to keep its members from drifting apart. The vine spans 13 million light-years. Its galaxies are moving. To stop them from scattering, something has to be pulling them inward with steady, patient force. The visible mass cannot do the job alone. It is too little to anchor a structure this large, which means there is more mass present than the team can see. A lot more. Enough to multiply the visible weight by a factor that has been the central mystery of cosmology for decades. The galaxies of the vine are riding on top of an invisible foundation many times heavier than themselves. That foundation has a name astronomers use carefully. Confirmed by gravity, never seen directly, holding everything together from the dark matter. And the vine, being so cleanly organized, gives the team a rare chance to map exactly where this invisible material is hiding. In the middle of the vine, near the densest knot of the bow, sits a galaxy the team simply called Galaxy A. It is enormous, one of the most massive members of the entire structure, a bulge-dominated giant, packed tight with stars at its core, with the kind of compact, heavy shape you usually only see in the modern universe after billions of years of slow assembly. Galaxy A should not exist yet. That is the simplest way to say it. The galaxy looks like the kind of thing that takes a very long time to build. It looks settled, mature, almost finished. And yet Webb is showing it to us in a moment of cosmic history when the universe is still young, when most galaxies are scrappy little blobs of new stars and bright gas. The team measured Galaxy A carefully and discovered something even stranger than its size. It had stopped making stars. Star formation in a healthy young galaxy is loud, bright, easy to see. Gas pours in, cools, collapses, ignites. Hot blue stars light up the spiral arms. The galaxy glows in the wavelengths that signal active stellar birth. You can read it in the spectrum the way you read activity in a beating heart. Galaxy A did not show that signal. The team measured a star formation rate of less than half a sun per year. For a galaxy of this size, that is essentially zero. The stellar nursery had been shut down. Astronomers have a term for this state: quiescent, or, more dramatically, quenched. The galaxy is alive in the sense that its stars still shine, but it has stopped giving birth to new ones. The hospital has closed its delivery rooms. This is one of the rarest things you can find in the early universe. Quenched galaxies are common today. Most of the giant elliptical galaxies in our cosmic neighborhood gave up making stars long ago. Their gas reserves ran dry. Their fires went out. They are old, settled, finished products of cosmic evolution. But 12 billion years ago, the universe was supposed to be in the middle of building everything. Galaxies should have been making stars at full speed. The idea that a giant like Galaxy A had already finished building itself, already exhausted its star-forming capacity, already settled into a quiet retirement, broke the expectation entirely. And Galaxy A was not the only one. A second giant nearby, Galaxy E, showed almost exactly the same signature: heavy, compact, bulge-dominated. Star formation effectively shut down. Two quenched giants, sitting in the densest part of the same forming cluster, in the same patch of cosmic time, both behaving like elderly galaxies in a young universe. That is not a coincidence. Two galaxies that look this similar, in this configuration, suggest a shared cause, something that happened to both of them around the same time, something violent enough to burn through their star-forming gas in a hurry, leaving them quiet ever after. The team had a working idea. It involved a much earlier event in the lives of these galaxies: a collision, a merger, a starburst so intense that it consumed the fuel supply almost overnight, leaving the giants depleted and dimmed. But before that idea could be tested, the team had to look closer at Galaxy E itself, because its quietness was, in its own way, even more puzzling than Galaxy A's. Galaxy E sits a short distance from Galaxy A along the spine of the vine. The two of them are close enough that, given a few 100 million more years of cosmic evolution, they will almost certainly fall into each other and merge. That is not the strange part. Big galaxies in dense regions merge all the time. The strange part is what Galaxy E looks like right now. It is a bulge, a round, dense, compact mass of stars packed tightly toward the center, with very little of the loose, sprawling, disk-like structure you would expect from a young galaxy still in the middle of its growth phase. In the modern universe, this kind of shape is associated with old galaxies, galaxies whose disks have been disrupted, whose gas has run out, whose stars have settled into a smooth, ball-shaped distribution after billions of years of gravitational mixing. We call them ellipticals, and they are the senior citizens of the cosmic galaxy population. Galaxy E looks like an elliptical, 12 billion years too early. When the team pulled the spectrum of Galaxy E and read the ages of its stellar populations, the picture sharpened. Most of the stars inside Galaxy E were already old at the moment Webb captured the light. They had formed in some earlier, even more ancient burst of activity, and had since settled into quiet middle age. The galaxy, in cosmic terms, was already past its prime. A galaxy that is past its prime in a universe only 2 billion years old is a paradox. The universe itself is still a child. Galaxies are supposed to be in their teenage years, full of star-forming chaos. Yet here is Galaxy E, looking like a retiree at a kindergarten. So, what happened to it? The team's best hypothesis points back about 500 million years before the moment Webb saw Galaxy E. That is the clock window when, they believe, Galaxy E underwent a major event. A merger with one or more other galaxies, most likely. Two big systems crashing into each other and combining. Mergers do violent things. They funnel huge amounts of gas into the center of the resulting galaxy. That gas gets compressed, heats up, and triggers a massive surge of star formation. A starburst. The galaxy lights up. Stars are born by the millions, all at once, in a frantic burning of fuel. The starburst is short. Cosmically speaking, it lasts a blink, but it consumes gas at a furious rate. A galaxy that goes through a major starburst can burn through most of its star-forming material in a tiny fraction of the time it would normally take. Once the burst ends, the galaxy is left depleted. Gas is gone. New star formation has nowhere to go. The fires die down. What Webb is seeing in Galaxy E may be exactly that aftermath. A galaxy that experienced a massive merger and starburst around 500 million years before, burned through its fuel in the process, and is now sitting quietly in the ash of its own former glory. Which raises a deeper question. What kind of environment can produce two galaxies like this, side by side, both quenched, both heavy, both sitting in the middle of the same forming cluster? The answer, the team began to suspect, was the vine itself. For decades, the textbook story of star formation went something like this. In the early universe, galaxies were busy, forming stars at high rates, burning bright, pulling in gas, growing fast. Star formation peaked somewhere around 3 to 4 billion years after the Big Bang, and then began a slow, gentle decline as the universe got older and gas supplies grew thinner. Quenched galaxies, by this story, were a late development. Galaxies that had run out of fuel or had their fuel removed by some disruptive event and had settled into quiet retirement. The numbers behind that story were calibrated against decades of observations from older telescopes. The picture seemed to hold up. Quenched galaxies were rare in the early universe and common in the late one, exactly as the model predicted. Then Webb came along. Galaxy A and Galaxy E, inside the cosmic vine, are two examples of something Webb has been finding more of as it pushes deeper into cosmic time. Massive, quenched galaxies, sitting in the early universe, behaving like they have already finished their main business of stellar production, not in small numbers either. The vine is one of the strongest concentrations of early universe quenched galaxies ever spotted. In fact, this is part of what makes the vine such a treasure for cosmologists. The team identified 11 quenched galaxies inside the structure. That is the largest collection of early universe quiescent galaxies ever found in a single cosmic environment at this redshift. A whole population of galaxies that, by the older textbook timeline, had no business being there. What this tells us is that the path from gas cloud to quiescent galaxy can run much faster than the old story allowed. Some galaxies in the early universe were not slow, patient builders. They were sprinters. They burned bright and burned out, all within the first couple of billion years of cosmic history. That has consequences far beyond the vine itself. If a noticeable fraction of early galaxies were doing this, then the standard mathematical models of how the universe assembles itself need adjustment. The gas-to-star pipeline must have been more efficient than we thought. The mechanisms that shut star formation down must have been faster, more aggressive, capable of acting on giants while they were still young. This is one of those moments in science where the data forces a rethink. Not a dramatic overthrow of everything, but a steady reshaping of details. The big picture still holds. Galaxies still form, evolve, merge. But the timing is wrong. The early universe was both faster and more efficient at producing mature-looking galaxies than the older models predicted. And the vine offers a particularly useful clue about why. The 11 quenched galaxies in the vine are not scattered randomly. They are concentrated in the densest, most central regions of the structure, the places where galaxies are packed closest together, where mergers happen most often, where the gravitational environment is most extreme. That is a strong hint. Whatever is killing star formation in these galaxies is connected to environment. Living inside a dense forming cluster, surrounded by other massive galaxies, exposed to constant gravitational interactions, seems to push galaxies toward early quenching. The vine gives us a place to study that process up close. 11 quiet giants, all in one structure, all telling the same story about how the early universe was building things faster than anyone expected. But to understand that process, we have to look at one of the most violent events those galaxies probably went through. A starburst is, in cosmic terms, a galaxy throwing the biggest party of its life and then collapsing, exhausted afterward. Under normal conditions, a galaxy makes stars at a steady, modest pace. A few solar masses worth per year, give or take, depending on its size. It is a slow, sustainable process. Gas comes in, cools, collapses, makes stars, and the cycle continues for billions of years. A starburst breaks all of that. During a starburst, a galaxy can produce hundreds, even thousands of solar masses worth of new stars per year. The galaxy lights up across every wavelength. It glows fiercely in the infrared as dust gets heated by all the new stellar activity. It shines in ultraviolet light from young, hot, massive stars. It pumps out energy that can be detected across the entire spectrum. But here is the catch. Starbursts are not sustainable. The galaxy is burning through its fuel supply at a furious rate. Gas that was supposed to last billions of years is being consumed in a few 100 million. When the gas runs low, star formation crashes. The party ends. The galaxy goes quiet, sometimes for the rest of its existence. This is exactly the kind of event the team suspects ran through Galaxy A in its earlier history. Picture it. Roughly 500 million years before the moment Webb captured Galaxy A's light, the galaxy was a different kind of object. Younger, wetter, loaded with gas. Then something happened. A merger with one or more nearby galaxies, most likely. The collision dumped enormous amounts of gas into the central regions of the resulting combined system. The gas compressed, heated, and ignited. A starburst tore through the galaxy. Stars formed at rates that would dwarf anything happening today. The center of the galaxy lit up like a furnace. New stellar populations exploded into being, grew, lived, and the most massive of them died as supernovae, blasting outward across the galaxy. Those supernovae did something important. They blew gas outward. They heated the surrounding interstellar medium. They disrupted the conditions needed for further star formation. Combined with the sheer rate at which the starburst was eating fuel, the supernova feedback finished the job. By the time the starburst ran its course, Galaxy A was depleted. Gas reserves were gone or scattered. the galaxy went quiet, and quiet it has stayed. Webb caught Galaxy A in this quiet phase. The starburst is long over. The young, hot stars are gone, having burned their short, brilliant lives. What remains is the vast population of slower, longer-lived stars that formed during the burst, now settled into a smooth, bulge-dominated shape, glowing with the soft red light of an aging stellar population. This story is a hypothesis, not a confirmed fact. The team cannot directly observe what Galaxy A was doing 500 million years before the moment Webb saw it. But the evidence fits. The shape of the galaxy fits. The age of its stellar populations fits. The presence of a likely merger partner sitting nearby in the same structure fits. If the hypothesis is right, then Galaxy A had its single most dramatic moment long before Webb arrived. The galaxy we see today is the calm afterward, the smoke from a fire that has already burned itself out. But there is one more wrinkle to this story, and it involves the second giant sitting right next door. Galaxy A and Galaxy E are not just neighbors. They are close enough that, given the gentle pull of gravity, they will almost certainly merge into a single, even more massive galaxy at some point in the next several 100 million years of cosmic evolution. And here is the interesting twist. The merger that the team thinks already happened in each of their separate histories may not have been their final merger at all. It may have been their first. Picture a sequence like this. 500 million years before the moment Webb captures their light, Galaxy A and Galaxy E are not yet the giants we see. They are smaller systems, each one assembled from the merger of two or more even smaller predecessors. Those earlier mergers triggered intense starbursts inside each of them. The starbursts burned through the available gas. The galaxies quenched. The result, by the time Webb's photons leave them, is two massive, quiet, bulge-dominated galaxies sitting close to each other in the densest knot of the vine. Now fast forward. Galaxy A and Galaxy E continue to drift toward each other under gravity. Their orbits decay. Eventually, they will collide. Two already quenched giants will smash together, scattering stars, briefly disturbing each other's shapes, and ultimately settling into a single enormous elliptical galaxy at the center of the cluster the vine is in the process of becoming. This is how the most massive galaxies in the present-day universe are believed to grow. Successive mergers, one after another, each one adding mass and removing star-forming gas, until what is left is a single huge ball of stars sitting at the heart of a galaxy cluster. The vine gives the team a chance to watch the early stages of this process up close. Galaxy A and Galaxy E are caught at exactly the moment when their first round of mergers and starbursts has finished, and the next round is starting to set up. This sequence also helps explain something puzzling about quenched galaxies in the early universe. The standard slow decline story for star formation cannot get galaxies to quench this fast, but the merger and starburst story can. Mergers compress gas, starbursts burn it, supernovae blow it out. The combination is fast and brutal, capable of taking a healthy young galaxy and shutting it down within a few 100 million years. In dense regions like the center of the vine, where galaxies are packed close and mergers are frequent, this fast-quenching pathway becomes much more likely. That is why the vine has 11 quenched galaxies sitting inside it, when isolated regions of space at the same redshift have almost none. Environment matters. The vine itself is what produced these quiet giants. The structure is, in a sense, eating its own contents, churning galaxies through repeated mergers, burning their gas, and leaving behind ever larger, ever quieter remnants. That is also why the team treats the vine as such a valuable laboratory. It is a rare chance to see the merger-driven assembly of massive galaxies happening in real cosmic time, in a region dense enough to make the process visible. What we see at the present epoch in the cores of nearby galaxy clusters, those huge old ellipticals at the very center, are the eventual descendants of objects like Galaxy A and Galaxy E. The vine is showing us the family album from billions of years ago. But the family album has more pages, and the next image in it is hiding inside the smaller galaxies along the chain. Imagine looking through an old photo album and finding a picture of someone who looks exactly like a person you know today. Same face, same expression, same age. But the photo was taken 60 years ago. That is something like what cosmologists feel when they look at Galaxy A and Galaxy E. Bulge-dominated, compact, quenched galaxies are common in the present-day universe. Walk through any nearby galaxy cluster and you will find dozens of these massive, quiet giants sitting near the center. They are the elders of the cosmic population. They have done their growing, finished their building, and settled into a comfortable old age. When astronomers look at one of these elders today, they are seeing the end product of a long history. Mergers, starbursts, quenching, slow drift toward the cluster center. Billions of years of cosmic processing. Now they are looking at Galaxy A and Galaxy E inside the Vine. And these two galaxies look essentially identical to those modern elders. Same compact shape, same bulge dominance, same quenched stellar populations, same cluster center positioning. The difference is when the Vine giants are showing us this exact appearance 12 billion years ago. The modern elders developed it slowly over the full age of the universe. The Vine giants developed it within the first 2 billion years. This is one of the most important things Webb has revealed about the early universe. The pathway to a mature-looking galaxy can be much shorter than anyone thought. Some galaxies, in the right environments, can compress the entire cosmic life cycle into a small fraction of the time the standard model would predict. That has implications for everything we thought we knew about how galaxies evolve. For a long time, the standard assumption was that the appearance of a galaxy was a reliable clue to its age. A young galaxy looked young, a mature galaxy looked mature. The two were easy to tell apart. Webb is showing that this assumption breaks down badly in dense environments like the Vine, where mergers and starbursts can age a galaxy in a hurry. This forces astronomers to be much more careful when they classify galaxies based on appearance alone. A bulge-dominated, quiescent galaxy might be ancient, or it might be a young galaxy that has lived hard and aged fast. Without redshift measurements and careful spectral analysis, you cannot tell from a picture alone. The Vine giants are also a warning sign about the limits of theoretical models. Many of the simulations astronomers used to predict galaxy evolution were calibrated against a universe that was supposed to grow gently and slowly in its early phases. Those simulations have a hard time producing galaxies like Galaxy A and Galaxy E this early. The simulations are being updated. The recipes for how gas turns into stars, how stars feed back on their surroundings, how mergers reshape galactic structure, are all being revisited in light of what Webb keeps finding. What is emerging is a more dramatic, more dynamic, more violent picture of the early universe. A cosmos where some galaxies grew in great explosive bursts, lived hard, quenched fast, and settled into mature appearances long before the universe itself had grown up. The Vine offers a particularly clean view of that more dramatic picture because it contains so many of these precocious giants in one place. But the giants are only part of the structure. Around them, scattered along the bow, the smaller members of the Vine are doing something quite different. Step back from the two big quenched giants for a moment. Look at the rest of the Vine. Most of the 136 confirmed members are not enormous. They are smaller galaxies, star-forming, active, many of them still ragged and irregular in shape, the way young galaxies tend to be. Some are bright knots of intense star formation. Others are softer, more diffuse. A few show clear signs of recent collisions, with disturbed shapes that suggest they have been bumped or partially merged with something nearby. These smaller galaxies are doing two things at once. First, they are growing, pulling in gas from the cosmic Webb filament running through the Vine, making stars, building up their stellar populations. Many of them will, given a few billion more years, become substantial galaxies in their own right. Second, they are falling, slowly, gently, but inexorably. The smaller members of the Vine are being dragged toward the dense central regions of the structure. Gravity from the four subgroups and especially from the central knot containing Galaxy A and Galaxy E, is pulling everything inward. The vine is collapsing on itself, very slowly, on cosmic timescales. This is how galaxy clusters build themselves. By eating their surroundings, picture the vine as a slow, patient predator. It has a body, a spine, several feeding mouths along the spine where the dense subgroups sit. Smaller galaxies around the structure are gradually drawn in along the filament, like prey approaching a slow-motion trap. As they fall toward the center, they pass through regions of denser galaxy population, where their chances of encountering and merging with another galaxy go up. Eventually, many of these smaller galaxies will not survive as independent objects. They will merge with each other. They will be absorbed into the central giants. They will lose their gas to the harsh environment of the cluster core, where intense gravitational interactions and heated gas can strip a smaller galaxy of its star-forming material. This is environmental quenching at work, not the explosive merger and starburst kind that produced Galaxy A and Galaxy E, but a slower, steadier process. As small galaxies fall toward the center, they get stripped of fuel, harassed by interactions, and their star formation gradually shuts down. By the time they settle into the central regions, they are quiet, quenched, ready to be absorbed into the building cluster. The vine, in this sense, is a galaxy machine. Smaller galaxies enter the structure as active, star-forming objects. They get processed by the cluster environment over hundreds of millions to billions of years. They emerge, eventually, as quenched, mature, cluster-resident galaxies. The team can already see this process at work. Some of the smaller galaxies in the vine show signs of being partway through environmental quenching. Their star formation rates are lower than similar galaxies in less dense environments. Their shapes are showing the early signatures of gravitational disturbance. They are being processed, slowly, steadily, in real cosmic time. What we are watching, in the vine, is not just a structure forming. It is a population of galaxies being reshaped by their environment. The vine is changing the galaxies that live inside it, not just hosting them. But the engine driving all of this is not the visible matter at all. The visible matter is along for the ride. The real architect lies underneath. If you removed every galaxy and every wisp of gas from the cosmic vine and left only what could be photographed in any wavelength, the image would be empty. Nothing visible to look at. A blank stretch of sky. But the vine would still be there. Underneath the galaxies, beneath the gas filament, around and through every visible piece of the structure, runs an invisible foundation made of something astronomers cannot see directly. They can only feel its gravity. They have been calling it dark matter for almost a century, and the vine is one of the cleanest places to study its handiwork in the early universe. Dark matter does not glow. It does not absorb light. It does not interact with normal matter in any of the usual chemical or electromagnetic ways. It only does one thing, as far as anyone has ever measured. It pulls, with gravity, steadily, patiently, across vast distances. In the early universe, dark matter clumped. Tiny variations in its initial distribution grew under gravity into denser regions, then denser still, building up invisible structures called halos. These halos are like wells in the fabric of space. Anything else falling nearby gets pulled in. Normal matter, the stuff that eventually becomes gas and stars and galaxies, fell into the dark matter halos that were already in place. Hydrogen pooled at the bottom of the wells. Stars ignited inside the pools. Galaxies grew from the inside out, riding on top of the dark matter scaffolding that had organized the territory long before. The vine is exactly this kind of arrangement, written large. When the team modeled the gravitational structure of the vine based on the motions and distribution of its galaxies, they confirmed what the physics required. There has to be a massive dark matter halo, or really a connected network of halos, underlying the entire bow shape. The visible mass alone cannot hold the vine together against the motions of its members. Something invisible, much heavier than everything visible combined, has to be doing the gravitational work. In the densest parts of the vine, especially at the central knot containing Galaxy A and Galaxy E, the team estimates The underlying dark matter halo is one of the most massive ever inferred for an early universe structure. The visible giants are sitting at the bottom of an enormous gravitational well that extends far beyond the galaxies themselves. This is what makes the vine so valuable. The dark matter is unusually concentrated, unusually organized, and unusually early. It is showing us exactly the kind of gravitational architecture cosmologists have spent decades arguing about. The vine is a real-world example of dark matter behaving exactly the way the standard model says it should, while also being assembled into a structure earlier than that same model predicted. The contradiction is not a flaw in dark matter theory. It is a flaw in the timing of how that theory has been applied to the early universe. Dark matter halos in the vine's region must have started clumping earlier or more aggressively than the textbook timeline allowed. Once the halos were in place, the visible matter followed naturally. Galaxies grew, stars ignited. The vine took shape. What we see today, 12 billion years after the fact, is the visible tip of an invisible iceberg. The galaxies are real. The gas is real. The dark matter, though invisible, is very, very real, and it built the entire structure. But the vine has a secret. It is not the only structure hiding in this patch of sky. The word the team keeps using to describe the vine is protocluster. It sounds technical, but the idea behind it is simple. A galaxy cluster, in the present-day universe, is the heaviest gravitationally bound structure that exists. Hundreds, sometimes thousands of galaxies, all swarming together inside a shared gravitational well. The largest clusters today contain quadrillions of solar masses worth of material. They are the cosmic mountains, the biggest things gravity has ever managed to assemble. A protocluster is what a cluster looks like before it has finished assembling. It is the embryo, the construction site. The eventual cluster, caught in the middle of pulling itself together, with parts still scattered along filaments and subgroups still settling into place. The vine fits this definition almost perfectly. Multiple subgroups of galaxies, a central dense knot with two giant members, smaller galaxies streaming along a filament toward the center, a massive dark matter halo underlying the entire shape. All the ingredients of a future galaxy cluster observed 12 billion years before that cluster will finish assembling. Astronomers have found a number of protoclusters in the early universe over the years, but most of the ones found before Webb were smaller, less organized, or harder to confirm. The vine is one of the cleanest, most clearly mapped, most populous early protoclusters ever identified. With 136 confirmed members, it is one of the richest samples of early cluster formation in the cosmic record. That richness gives the team something rare: a statistical population, 11 quenched galaxies, scores of star-forming members, 4 subgroups, a clear filament, a dark matter scaffold, enough data to actually study how an early cluster builds itself, instead of just seeing 1 or 2 pieces of the process. The vine will not stay a vine forever. Cosmic evolution has a clear trajectory for structures like this. Over the next several billion years after the moment Webb captured, the 4 subgroups will continue to fall toward each other. They will merge. The central knot, containing Galaxy A and Galaxy E, will absorb the surrounding smaller galaxies. The bow shape will collapse inward. The filament will be consumed. By the present-day moment in cosmic time, the vine should have transformed completely. The eventual descendant is likely a massive galaxy cluster, hundreds or thousands of galaxies, a central giant elliptical galaxy formed from the merger of Galaxy A, Galaxy E, and other big members, a hot atmosphere of intracluster gas, the full setup of a mature cosmic cluster sitting somewhere out in the present-day universe, completely invisible to us because the light from that current state has not had time to arrive at Earth yet. In a strange way, that means the vine has 2 existences. There is the early stage structure Webb is showing us, and there is the modern descendant cluster that exists right now in cosmic terms, but that we cannot see yet. For the team, this is the most exciting part. The vine is not just a curiosity, it is a window into how clusters in our own neighborhood once began. Our local universe is full of mature galaxy clusters. Each of them must have started as something like the vine billions of years ago. Webb is showing us the family origin stories of the giants. But there is a complication. The vine is not the only structure in this patch of sky. Behind it, fainter, hidden in the same Webb data, lies something the team did not expect. Imagine watching a city grow from above, in time-lapse. Houses appear, roads connect, neighborhoods expand. Eventually, a metropolis stands where there had been only scattered settlements. Now, run the same time-lapse on the cosmic vine. Start with the vine as Webb sees it today, 12 billion years ago, bow-shaped, stretched. 4 subgroups, central knot, smaller galaxies streaming inward, a protocluster in mid-assembly. Press play. Over the next billion years of cosmic time, the smaller galaxies along the filament accelerate inward. The bow shape contracts. The 4 subgroups draw closer together. Star formation in many of the infalling galaxies begins to slow as they enter denser regions. The central knot grows heavier. Galaxy A and Galaxy E continue their slow gravitational dance toward each other, edging closer, their orbits decaying with each pass. A few billion years in, the structure has changed dramatically. The bow has collapsed inward. The filament is mostly absorbed. The 4 subgroups have merged into one larger central concentration. Galaxy A and Galaxy E, after a series of close encounters, finally collide and merge. The combined object is a single, enormous, elliptical galaxy, sitting at the heart of what is now clearly a galaxy cluster. Around it, hundreds of smaller galaxies orbit in chaotic paths. The intergalactic space is filled with hot, thin gas, heated to millions of degrees by the gravitational compression of the cluster's growth. The dark matter halo that held everything together has compacted further, deepening the gravitational well at the center. By the time the cosmic clock reaches the present epoch, the vine has finished its transformation. Where Webb sees a curving chain of galaxies, our descendants in some far future would see a fully mature cluster. Hundreds of trillions of solar masses, possibly more, a genuine cosmic giant. The team has done careful modeling on this trajectory. Based on the current mass of the vine, the rate at which it is pulling in surrounding material, and the structure of its dark matter halo, the eventual descendant cluster should rank among the more massive galaxy clusters in the universe. Not necessarily the absolute heaviest, but in the upper tier, comparable to or heavier than some of the most famous nearby clusters. That forecast is one of the things that makes the vine so important. Most of the well-studied galaxy clusters in our cosmic neighborhood are already finished product. We see them as they are now, mature and settled. We do not get to watch them grow. The vine gives us a forecast we cannot watch unfold in real time, but we can model with high confidence. The physics is well understood. The starting conditions are well measured. The future of this structure is one of the more confident predictions cosmology can make about a specific object. This kind of forward modeling has practical value. It tells cosmologists what kinds of clusters to expect to find in the present-day universe at certain mass scales. It helps tune the simulations that try to reproduce the entire history of cosmic structure formation. The vine is a benchmark, a real example of an early cluster that can be tracked, in theory, all the way through to its mature form. But the vine has another piece of evidence to offer. Behind it, hovering in the same region of sky, sits a second structure the team had not been looking for. And that second structure changes the picture in ways nobody anticipated. When the team finished mapping the cosmic vine and sat down with the full dataset, they began to notice something odd in the background of the same region. A scattering of galaxies that did not quite belong to the vine. Their redshifts were close, but not identical, a little smaller, about 3.34, instead of the vine's 3.44. That difference, while it sounds tiny, translates into a real cosmic separation. The galaxies were not part of the same structure. They were sitting in a different layer of cosmic time, slightly closer to us, slightly more recent in the universal history. But there were a lot of them, 47, by the team's eventual count. 47 galaxies, all sharing nearly the same redshift, all clustered in the same patch of sky as the vine, distributed in a softer, more diffuse pattern, not a tight chain, more of a veil. a second structure, fainter and more spread out, hovering in front of the vine at a slightly closer cosmic distance. The team named it the leaf. The naming was deliberate. The vine was a tendril. The leaf was the softer, broader structure attached nearby. Together, they painted a picture of cosmic vegetation growing in the deep dark, with the vine as the main stem and the leaf as a delicate, layered overlay. The leaf is not a fully assembled cluster. It is more like a loose group of galaxies, organized into two smaller subgroups within the larger structure, less massive than the vine, less concentrated, but still real, still gravitationally connected, still doing its own slow assembly process. What makes the leaf important is what its presence implies. In a single Webb pointing, the team had now identified two large-scale structures sitting at very nearly the same cosmic moment, in the same small patch of sky. Not one impressive find, but two, stacked along the same line of sight, separated by a relatively small slice of cosmic distance. Statistically, this is a striking result. The early universe was supposed to be sparser in this kind of large structure. Finding one big formation in a deep field is notable. Finding two, almost overlapping, in the same field suggests the early universe was producing structures at a higher rate than the older models predicted. The leaf also gives the team something else useful, a comparison case. Two structures at similar redshifts, in the same patch of sky, observed with the same instrument under the same conditions. That is a cosmologist's dream setup. You can hold environment relatively constant and look at how two different structures of different masses are evolving side by side. Early comparisons already show interesting differences. The vine, with its dense core and multiple quenched giants, is further along in its assembly. The leaf, less concentrated, has fewer quenched members and more star-forming galaxies. Both are protoclusters, but they are at different stages of the same general process. Together, the vine and the leaf are starting to tell a story that goes beyond either structure alone. They are showing us that the early universe was busy building large structures at multiple stages of completion, in close proximity, all at once. And that observation lands directly on top of the standard cosmological model in a way that is hard to brush aside. Consider the size of the patch of sky the team was looking at. The Webb observations of the extended growth strip cover a small fraction of the total sky, a narrow window, focused tightly on this one region. It is the kind of pointing astronomers use when they want maximum depth at the cost of sky coverage. A deep core sample, taken from a single spot. In that small core sample, the team found two large-scale structures, the vine and the leaf, both substantial, both populous, both early, both sitting at redshifts, placing them within a fairly narrow slice of cosmic time. If you take the standard cosmological model and ask how often you should expect to find a structure as big as the vine in any given patch of sky at this redshift, the answer is rare. Not impossible. The model can produce them, but the rate at which they are predicted is low. They should be unusual finds, scattered widely across the sky, hard to come by. Now ask how often you should expect to find two such structures in the same small patch of sky, sitting at nearly the same redshift. The answer drops sharply. The probability, based on standard predictions, is quite low. Yet, here it is. Two structures, same patch, same error, confirmed by careful spectroscopy, mapped by detailed photometry, locked down by 183 confirmed galaxy memberships across both structures combined. This is the kind of result that makes cosmologists pay attention. A single oddity can be dismissed as a statistical fluke. The universe is huge. With enough sky, you will eventually find rare configurations just by chance. One unusually large early structure, by itself, does not necessarily break any model. It is just a tail event. Two such structures, side by side, raises the bar. The probability of two tail events overlapping in the same small region of sky is much smaller than the probability of one. It starts to look less like coincidence and more like a hint that the underlying model is missing something. Webb has been finding more of this kind of evidence over its operating life. Other deep fields have turned up other unexpectedly massive early structures, quasars from too early in cosmic history, galaxies more mature than they should be. Now, in the extended Groth strip, two protoclusters layered along the same line of sight at nearly the same cosmic moment. The pattern is becoming hard to ignore. The implications are not small. If the early universe was producing large structures faster, more often, and in more places than the standard model predicts, then the model has to be adjusted. Possibly in the way it treats dark matter clumping, possibly in the way it treats the initial conditions of the Big Bang, possibly in some deeper way involving the fundamental physics of how mass behaves at cosmic scales. These are open questions. The team behind the Vine and Leaf studies is careful not to overclaim. They report the structures, the masses, the redshifts, the membership counts. They let the broader cosmology community wrestle with what it all means. But the wrestling is real. Conferences are full of debates about what Webb is finding. Papers are appearing every month proposing tweaks, adjustments, or larger revisions to the standard model. The Vine and the Leaf are sitting at the center of that conversation. Two structures that should not coexist in this configuration this early, observed cleanly, measured carefully, demanding an explanation. Roll the clock back, way back, to the moment just after the Big Bang. Standard cosmology paints the very early universe as a hot, dense, almost perfectly smooth soup. Particles everywhere, energy everywhere, tiny variations in density, but nothing dramatic. The whole cosmos, on every scale you could measure, was startlingly uniform. We have direct evidence for this smoothness. The cosmic microwave background, the leftover radiation from the early universe that still permeates space, is one of the most uniform things ever measured. Look at it across the entire sky and the temperature varies by only about 1 part in 100,000, a near-perfect haze of warmth, identical in every direction. That smoothness is the starting condition for everything that comes after. From those tiny variations, gravity went to work. Slightly denser regions attracted more material. Slightly emptier regions lost material to their neighbors. Over hundreds of millions of years, the density contrasts grew. Dense regions became denser, empty regions became emptier. The smooth soup began to fracture into a structured pattern. The standard prediction is that this process is slow, patient, hierarchical. Small things form first, tiny dark matter halos, then small galaxies, then bigger galaxies, then groups. Eventually, much later, full clusters. By the time the universe was 2 billion years old, the standard model expects to see plenty of small galaxies, some growing larger ones, scattered groups, and the early stages of larger structures forming, but fully organized protoclusters with hundreds of confirmed members, weighing hundreds of billions of solar masses, with quenched giants already settled at their centers, are not part of the typical expected inventory at that epoch. And yet, the Vine, this tension between prediction and observation, is what makes Webb's findings so important. The standard model has been remarkably successful at explaining the universe over many decades. It predicts the cosmic microwave background, the abundance of light elements, the large-scale structure of the modern universe, and many other observations to high precision. It is not wrong in any obvious way, but it might be incomplete in some specific way, or it might need its parameters retuned, or it might be missing a piece of physics that becomes important only in certain situations, like the rapid early growth of the largest structures. This is how science usually progresses. The dominant model holds up across most observations, then a new instrument reveals a place where the model strains. Researchers investigate. They propose adjustments. They test the adjustments against other observations. Slowly, the model evolves. Sometimes the changes are small. Sometimes they reshape entire fields. Webb is forcing exactly this kind of process to play out for early universe cosmology right now. The Vine is one piece of evidence among many. Other deep fields are turning up other puzzles. Together, they are building a case that the early universe was busier, more dynamic, and more capable of building large things than the older textbooks allowed. For working cosmologists, this is one of the most exciting moments their field has had in years. Real puzzles, real tension between prediction and observation, real possibilities for new physics or new refinements. For the rest of us, the takeaway is simpler. The universe, as Webb is showing us, has a more dramatic origin story than we used to believe. Things came together faster than we thought. Structures appeared sooner. The cosmic dawn was more violent and more productive than the calmer picture we had drawn. And the vine is a lead character in that revised story. The cosmic vine is not an isolated discovery. It belongs to a growing collection of Webb finds that have, together, started to pile up evidence for a more aggressive early universe. A short tour of the collection is worth taking, because it puts the vine in context. Webb has been finding galaxies that are too massive too early. In its first months of operation, the telescope identified candidate galaxies at extreme redshifts that already contained billions of solar masses worth of stars. By the standard model, galaxies that big should not have had enough time to assemble. The findings were startling enough that some researchers initially questioned the redshift estimates. Follow-up spectroscopy confirmed many of them. Webb has found ancient supermassive black holes. Black holes weighing millions of solar masses, sitting at the centers of galaxies that existed within the first billion years of cosmic history. These black holes also pose a timing problem. Standard models for black hole growth struggle to produce something that massive that early. Webb has found unusually mature galaxies in unusually early epochs. Galaxies with disk structures, bulges, and quiescent stellar populations that look like they belong in a much older universe. The Vine giants, Galaxy A and Galaxy E, fit squarely into this category. Webb has found large-scale structures earlier than expected. The cosmic vine is one of the cleanest examples, but other early protoclusters have been identified in other deep fields. Each one adds another data point to the picture of an early universe that was building big things faster than predicted. Taken individually, any one of these findings could be a quirk, a statistical fluctuation, an observational error, an overlooked detail. Taken together, they form a pattern that is hard to dismiss. The early universe was not the gentle, slow-growing place the older textbooks described. It was a place where mass clumped quickly, where galaxies grew aggressively, where black holes appeared early, where large-scale structures organized themselves on shorter timescales. The cosmos was efficient, productive, capable of building giants long before anyone gave it credit for doing so. This collective Webb evidence has triggered a wave of theoretical work. Researchers are exploring multiple possibilities. Maybe dark matter behaves slightly differently in the early universe than the standard models assumed. Maybe star formation efficiency was higher in the early eras, allowing galaxies to grow stellar mass faster from the same gas supply. Maybe black holes formed through pathways that are not yet fully understood. Maybe the initial conditions left over from the Big Bang were less smooth than we measured, with more substantial seeds for early structure. Each of these possibilities is being tested against the full range of available data. The standard model does not fall easily. It has to be challenged on multiple fronts before any major revision becomes accepted. But the challenges are mounting. Webb is providing the evidence. The theorists are doing the work. Within a few years, this collective effort may produce a refined version of the cosmological model that better accommodates Webb's findings. Or it may produce something more dramatic, a genuine revision to how we understand the early universe. Either way, the science will be stronger for the encounter. The vine sits in the middle of this turbulence as one of the cleanest, best-mapped examples of the puzzle. Whatever the resolution turns out to be, structures like the vine will be part of the explanation. But to find such structures in the first place, Webb had to be able to see them. And the way Webb sees is unlike anything that came before. The reason the vine had been hiding for so long comes down to a single problem: dust. Galaxies in the early universe produce enormous amounts of dust. Tiny grains of solid material, no bigger than smoke particles, scattered throughout interstellar space. This dust does something inconvenient to anyone trying to study early galaxies. It absorbs visible light. It absorbs ultraviolet light. It blocks the wavelengths that earlier telescopes were built to see. For older instruments like Hubble, looking at heavily dust-obscured early galaxies meant trying to see through a thick veil. Some light got through, some did not. Many galaxies were either invisible or appeared misleadingly faint, because the dust was eating most of their visible wavelength signal before it ever reached the telescope. Webb solves this problem by changing wavelengths. Infrared light, the kind of radiation Webb is built to detect, passes through cosmic dust much more easily than visible light. Where visible light gets blocked, infrared light slips through. A galaxy hidden behind dust at visible wavelengths can shine clearly at infrared wavelengths. The veil becomes transparent. There is a second reason infrared is the right tool for early universe work. Redshift. Light from very distant galaxies gets stretched on its long trip toward Earth. Light that left a galaxy as visible or ultraviolet billions of years ago arrives at Earth shifted into the infrared. Even galaxies that originally produced their main light at shorter wavelengths now show up most strongly in the infrared. So Webb's infrared eyes do double duty. They pierce through dust, and they catch the red-shifted light of the most distant galaxies. For studying the early universe, no other instrument has the same combination of capabilities. For the cosmic vine, this combination was decisive. Many of the smaller, dust-obscured members of the structure had been invisible or barely visible in earlier observations of the extended Groth strip. They simply did not show up clearly enough in visible wavelength data to be identified as members of a coherent structure. Webb pulled them into focus. The chain of galaxies that had been hidden by a combination of dust and redshift suddenly stood out cleanly in the infrared images. Webb also has resolution and sensitivity that older infrared instruments did not. Earlier infrared telescopes existed, but they were smaller, less sensitive, and could not produce the sharp, detailed images Webb provides. Webb combined the right wavelengths with the right size and the right precision to make findings like the vine possible for the first time. This is why Webb has been transforming the field of early universe astronomy. Not because it is doing something fundamentally new in concept, but because it is doing something old in execution at a much higher quality level than anything that came before. It can see fainter, sharper, and through more dust. That extra capability is what brings hidden structures like the vine into view. Future instruments will push further. The Nancy Grace Roman Space Telescope, scheduled to come online in the next few years, will provide a wider field of view at similar wavelengths. It will be able to survey larger areas of sky in less time, finding many more structures like the vine across many more deep fields. The Extremely Large Telescope, a ground-based observatory under construction, will provide even more detailed follow-up observations of individual interesting targets. Webb is the first chapter in a longer story of infrared exploration. The vine will not be the last hidden giant pulled out of the dark. Webb is not a single eye. It is a collection of instruments, each one specialized for a different kind of work. The two instruments that did most of the heavy lifting for the cosmic vine discovery are NIRCam and NIRSPEC. The names are short for Near-Infrared Camera and Near-Infrared Spectrograph. Together, they form the imaging and analysis core of Webb's near-infrared capability. NIRCam is the camera. It produces the deep, sharp infrared images that map regions of sky in fine detail. When the team scanned the extended Groth strip looking for early galaxies, NIRCam was the instrument doing the looking. It captured the broad picture. It revealed the galaxies. It produced the images that first showed the bow-shaped chain. NIRCam is sensitive across a range of near-infrared wavelengths, which lets it pull out galaxies of different types at different redshifts. A galaxy that is faint in one wavelength might be bright in another. By imaging in multiple bands, NIRCam builds up a multicolor picture that gives initial clues about each galaxy's distance and properties. But initial clues are not enough for serious science. To confirm the nature of each galaxy and lock down its redshift precisely, the team needed spectroscopy. That is where NIRSPEC comes in. NIRSPEC takes the light from a galaxy and breaks it apart into its component wavelengths. The result is a spectrum, a kind of fingerprint that reveals what the galaxy is made of, how fast it is moving away, how much star formation is happening inside it, and how far back in time the light originated. For the vine, NIRSPEC produced spectra for the brightest members of the structure. Those spectra confirmed that the galaxies all sat at nearly the same redshift, around 3.44. They confirmed that Galaxy A and Galaxy E had quenched stellar populations. They provided the precise measurements that turned a suspicion into a published result. A third Webb instrument, MIRI, the mid-infrared instrument, also contributed. MIRI works at longer infrared wavelengths than NIRCam and NIRSpec, sensitive to warm dust and to certain features of older stellar populations. For some of the Vine's quenched giants, MIRI data helped confirm the dust content and the age of the stars. Beyond the Webb data itself, the team relied on archival observations from earlier telescopes, Hubble images of the same patch of sky, ground-based spectroscopy of some of the brighter galaxies, sub-millimeter observations from radio facilities that detect cold gas. All of it was layered together with the Webb data to produce the complete picture of the Vine. This kind of multi-wavelength, multi-instrument analysis is how modern astronomy works. No single telescope, no matter how powerful, gives the full story. Webb provides the dominant new information, but it builds on decades of prior work. The Vine was discovered with Webb, but it was understood by combining Webb with everything that came before. Behind the instruments themselves stands a small army of engineers, calibration specialists, software developers, and data analysts. Webb is one of the most technically demanding instruments ever built. Keeping it operating, processing its data, and turning raw signals into reliable scientific results requires constant work by hundreds of people. The Vine paper, when it eventually appeared, listed many authors. Each one contributed something to the result. Behind them stood the much larger community that built and operates Webb. The discovery of a single cosmic structure rests on a vast pyramid of human effort. That effort made the next part possible: the careful, galaxy-by-galaxy redshift mapping that turned the Vine from an interesting smear into a confirmed structure. When the team first spotted the curving chain of galaxies in the Webb images, they had a suspicion. The galaxies looked like they belonged together. Their colors, brightness, and distribution all hinted at a coherent structure. But hint is not the same as proof. To turn the suspicion into a confirmed discovery, the team needed redshift measurements for every member of the chain, not estimates, not rough guesses. Real spectroscopic redshifts, locked down to high precision for as many galaxies as possible. There are two main ways to measure a galaxy's redshift. One is fast and approximate. The other is slow and precise. The fast method is called photometric redshift. It works by measuring the brightness of a galaxy in several different wavelength bands and comparing the resulting color pattern to template galaxies of known redshift. If the pattern matches a galaxy at, say, redshift 3.4, then the new galaxy is probably also at about that redshift. Photometric redshifts are quick. They can be calculated for thousands of galaxies in a single image, but they are also fuzzy. The uncertainty on a single photometric redshift is usually large, often around 10%. Good enough for surveys, not good enough to confirm membership in a specific structure. The slow method is called spectroscopic redshift. It involves taking a full spectrum of each galaxy and identifying specific spectral features, like the absorption or emission lines of common elements. By measuring exactly how much those known features have shifted in wavelength, you can pin down the galaxy's redshift to high precision, often to 4 or 5 decimal places. Spectroscopic redshifts take time. Each galaxy requires its own spectrum, which means dedicating valuable telescope time to each individual target. For a structure like the Vine, with 136 members, this is a major investment of effort. The team did the work. They pulled spectra from the Webb data for as many Vine members as they could. For galaxies too faint for direct spectroscopy, they used the sharpest available photometric redshifts. The combination produced a precise map of which galaxies were members of the Vine, which were members of the Leaf, and which were unrelated foreground or background objects. The result was the confirmed membership count: 136 galaxies in the Vine itself, 47 in the Leaf, all sitting at their proper places along the cosmic distance scale. This kind of careful work is what separates a real discovery from speculation. Without the spectroscopic redshifts, the Vine could have been argued away as a chance alignment of unrelated galaxies along the same line of sight. With the redshifts confirmed, the structure became undeniable. Every member sat at the same cosmic distance. The shape was real, the mass was real, the structure was real. The team also identified 4 subgroups within the vine and 2 subgroups within the leaf, based on the detailed redshift and spatial distribution of confirmed members. These subgroups are the local concentrations of mass that act as growth centers for the larger structures. They represent the next level of detail in understanding how the vine is assembling itself. Each subgroup will eventually merge with the others to form the central core of the future cluster. Watching them in the Webb data lets the team study the early stages of this process up close. But the headcount of confirmed members is not done growing. With every new round of analysis, the membership numbers climb. The first paper announcing the cosmic vine reported about 20 massive galaxies in the structure. That number was based on the brightest, most easily identified members, the ones that stood out clearly in the initial Webb images. Subsequent analyses dug deeper. As the team and other researchers looked more carefully at the same data, they pulled out fainter members, smaller galaxies, lower mass companions. Each new layer of analysis added more confirmed members to the structure. By the most recent careful study, the headcount had grown to 136 spectroscopically confirmed vine galaxies, plus another 47 in the leaf. That is more than 180 galaxies total, in 2 structures, in one small patch of sky. And the number is almost certainly still incomplete. There are likely more members of the vine that have not yet been confirmed. Some are too faint for current spectroscopy. Some sit on the edges of the structure, where membership is harder to determine. Some may be hidden behind dust that even Webb cannot fully penetrate. The true membership of the vine, including all the small galaxies that gravity has bound to the structure, may run into several hundred objects. This is one of the things that makes large-scale structure work so labor-intensive. Each galaxy needs to be confirmed individually. The work cannot be rushed. New observations, new analysis methods, and new follow-up campaigns will continue to refine the membership count for years to come. The eventual descendant cluster, the one the vine will become billions of years after the moment Webb captured, will likely contain thousands of galaxies. Most of them are not yet visible to us, because they have not yet been pulled into the structure. They are still spread out across the surrounding region, slowly migrating inward under the gravitational pull of the forming cluster. What Webb sees as the vine is just the central, most developed part of a much larger cosmic neighborhood that is in the process of building a galaxy cluster. The full neighborhood extends well beyond the bow shape itself, with smaller galaxies and gas filaments stretching outward in directions the team has not yet fully mapped. Future observations will fill in this larger picture. The Roman Space Telescope, with its wider field of view, will be especially valuable for mapping the broader environment around protoclusters like the vine. By surveying larger swaths of sky at similar wavelengths to Webb, Roman will be able to identify the full extent of the surrounding galaxy population that is destined to fall into the vine over cosmic time. For now, the 136 confirmed vine members are enough to support detailed analysis. They give the team a real population of early galaxies to study. Their masses, their star formation rates, their morphologies, their environments, and their gas contents all become accessible to detailed measurement. The 11 quenched galaxies in the vine, in particular, form the largest known sample of early universe quiescent galaxies in a single overdense region. That sample is unusually valuable. It lets researchers study how quenching works in dense early environments with statistical confidence, instead of relying on 1 or 2 example galaxies. This statistical advantage is one of the reasons the vine has become such a focus of current research. It is not just an interesting object, it is a usable laboratory, big enough to support real population studies, clean enough to give clear results, important enough to justify the substantial telescope time being invested in it. And the most interesting region of that laboratory is the tight central knot, where the densities reach their peak. Most of the universe, even at the redshift of the vine, is fairly empty. Galaxies are spread out. Distances between neighbors are large. The average density of cosmic matter is low. The vine is not average, especially at its core. When the team measured the density of galaxies in different parts of the vine and compared it to the density of galaxies in surrounding regions of the sky at the same redshift, the central knot stood out dramatically. The number of galaxies per unit volume in the densest part of the vine ran 2 to 3 times higher than the field average. For the most massive galaxies in particular, the contrast was even more striking. This kind of overdensity is significant. It means the vine is not just a coincidental lineup of nearby galaxies. It is a real concentration, a place where gravity has been gathering galaxies together with measurable efficiency against the general spreading out that the expansion of the universe normally produces. The overdensity also has consequences for the galaxies that live in it. Living in a dense environment changes the way a galaxy behaves. Encounters with neighbors become more frequent. Gas can be stripped away by interactions with the surrounding intergalactic medium. Mergers happen more often. Star formation can be either triggered or shut down, depending on the specifics of each interaction. The 11 quenched galaxies of the Vine are clustered in exactly the regions of highest density. This is not a coincidence. The dense core is where the merger rate is highest, where the starburst and quench cycle runs fastest, where galaxies get processed most aggressively by their environment. The quenched galaxies are the survivors of that processing, the ones that have been through the ringer and come out as quiet, mature giants. Less dense parts of the Vine, out toward the ends of the bow, host more star-forming galaxies. The processing has not yet reached them with full intensity. They are still actively growing, still making stars, still in the early stages of being absorbed into the larger structure. This density gradient gives the team a natural experiment. By comparing galaxies at different distances from the dense core, they can study how environment shapes galaxy evolution, all within a single structure where many other variables are held constant. It is one of the cleanest setups for environmental galaxy evolution work that the early universe provides. The density of the Vine's core is a hint about the underlying dark matter halo as well. Visible galaxies are traces of the deeper gravitational structure. Where galaxies pile up, dark matter is also piling up. The fact that the Vine's core is unusually dense in galaxies means it is also unusually dense in dark matter. The gravitational well is deep there. This depth has a useful consequence for theory. Cosmologists can use the Vine to test predictions about how dark matter halos grow in the early universe. The Vine's central halo, based on the team's modeling, is one of the more massive halos confidently identified at this redshift. That makes it a benchmark for testing how often and how massive such early halos should be in different cosmological models. Most standard models predict that halos this massive should be rare at this redshift. Finding one is interesting. Finding it inside a fully assembled protocluster surrounded by quenched giants makes it doubly interesting. The Vine's core is one of the strongest individual pieces of evidence that the early universe was building deep gravitational wells faster than the textbooks expected. And around those wells, the galaxies caught in them were going through changes that cosmologists are still trying to fully understand. The word quenching keeps coming up. It is worth pausing to look at it carefully. A galaxy quenches when its star formation effectively stops, not slows down, stops. The galaxy still contains all the stars it has already produced, and those stars continue to shine for billions of years afterward. But no significant new stars are being added. The factory has shut down. There are a number of ways a galaxy can quench. Each one operates on different timescales and through different mechanisms. One pathway is gas exhaustion. A galaxy converts its available gas into stars over time. Once the gas runs out, star formation has nothing left to work with. This is the slow, gentle pathway. It can take billions of years. Another pathway is gas removal. External processes can strip gas out of a galaxy. Strong gravitational interactions with neighbors. The hot atmosphere of a galaxy cluster pushing through a galaxy as it falls inward. Powerful outflows driven by supernova explosions or active black holes. These processes can be quick. They can quench a galaxy in just hundreds of millions of years. A third pathway is heating. If the gas inside a galaxy gets heated to high enough temperatures, it cannot cool and collapse to form new stars. Energy injection from supernovae, radiation from nearby massive stars, or feedback from a central black hole can all contribute to this heating. If the heating is sustained, the galaxy stays quenched. A fourth pathway involves morphological changes. When a galaxy undergoes a major merger and its disk gets disrupted, the resulting bulge-dominated structure makes it harder for the remaining gas to collapse and form new stars. The galaxy is reshaped into a configuration that resists star formation, even if some gas is still available. In real galaxies, all of these mechanisms can operate together. A merger triggers a starburst that exhausts most of the gas. The resulting bulge structure makes further star formation difficult. A central black hole becomes active and heats whatever gas is left. The galaxy quenches through the combined effect of multiple processes. For Galaxy A and Galaxy E inside the Vine, the team suspects exactly this kind of combined quenching. Mergers reshape them, starbursts burn through their gas. Feedback from the resulting activity heated and removed what gas remained, and the bulge-dominated configurations they ended up with made it hard to start star formation again. The whole sequence had to happen within the first 2 billion years of cosmic history. That is the timing that makes the Vine giants so striking. Star formation had to ramp up, peak, exhaust the gas, and shut down, all on a much faster schedule than the standard slow quenching pathway would allow. This is why the Vine matters for theoretical work. It is forcing astronomers to take fast quenching seriously as a major pathway in the early universe. The slow, gradual quenching that dominates in the present-day cosmos was not the only mode of operation in earlier eras. In dense environments like the Vine, fast quenching may have been common, even normal. Updated galaxy evolution models are being developed to incorporate this. The new models allow for higher merger rates in early dense environments, more efficient starbursts, more aggressive feedback, and faster transitions from active to quenched. These updates are improving the agreement between simulations and Webb observations. What we are seeing is science adjusting to new evidence in real time. The Vine is one of the cleanest test cases. It provides a real-world example that any updated model has to be able to reproduce. But there is one more piece of the quenching puzzle that the team is paying close attention to: the role of supermassive black holes. Most large galaxies, including all the giant ones in the present-day universe, contain a supermassive black hole at their center. These black holes range from millions to billions of times the mass of our Sunday. They sit quietly most of the time, but when they are actively feeding on surrounding gas, they become some of the brightest objects in the universe. These active black holes are called active galactic nuclei. Their feeding activity releases enormous amounts of energy. That energy can heat surrounding gas, drive it outward in powerful winds, and disrupt the conditions needed for star formation across large parts of the host galaxy. This process is called feedback. In the context of galaxy evolution, it is one of the leading suspects for how galaxies quench. A central black hole, given enough fuel, can shut down star formation in its host galaxy by disrupting the gas supply. For Galaxy A and Galaxy E in the Vine, black hole feedback is one of the candidate explanations for why the galaxies quenched as fast as they did. Both galaxies are massive enough to plausibly host supermassive black holes. If those black holes were active during the relevant epoch, they could have helped drive the rapid quenching that the team observes. Direct evidence is harder to pin down. Active black holes produce specific signatures in their light, including certain emission lines and excess radiation in particular wavelengths. Detecting those signatures in galaxies as distant as the Vine is challenging. The team has been working on it, but firm conclusions about whether Galaxy A and Galaxy E hosted active black holes during their quenching phases are still pending. What the team can say is that black hole feedback is consistent with the observations. The galaxies look like they quenched fast. Black hole feedback is one of the few mechanisms known to be capable of fast quenching in massive galaxies. The presence of active black holes during the relevant era would help explain what Webb sees today. This is an area of active research. Webb itself is being used to look for active black holes in the early universe. So far, the surveys have been finding more of them than expected. Like so many other early universe phenomena, black holes appear to have been more common, more active, and more important during the early eras than older models predicted. If active black holes were widespread in early massive galaxies, then their feedback effects would have been widespread too. Many of the early quenched galaxies that Webb keeps finding may have been quenched, at least in part, by their central black holes. The vine giants would then fit naturally into this broader pattern. The implications run beyond the vine itself. Black hole feedback is one of the most important regulating processes in galaxy evolution. Understanding how it operated in the early universe is essential to understanding why galaxies look the way they do today. Webb is providing data that sharpens this understanding considerably. For the vine specifically, the question of whether black hole feedback was the dominant quenching mechanism is still open. The combination of mergers, starbursts, supernova feedback, and black hole feedback is hard to disentangle in any individual galaxy, especially at high redshift. But the pieces of evidence are accumulating, and the team is working on better measurements. What is already clear is that the early universe was a more energetic, more violent, more dynamic place than the older models suggested. Webb is showing us a cosmos in the middle of intense growth, with multiple processes operating at high intensity to shape the galaxies we see. And these findings have implications for our own cosmic backyard. The cosmic vine is far away in space and time, but it is also a window into the past of our own cosmic neighborhood. The Milky Way sits in a cosmic environment called the local group. We share this region with the Andromeda Galaxy and a number of smaller dwarf galaxies, all bound together by gravity, drifting through a quieter region of the cosmic web. The local group is not part of any major galaxy cluster. It sits in a relatively low-density environment compared to places like the Virgo cluster or the Coma cluster. Our cosmic neighborhood is a loose, modest grouping rather than a dense, massive concentration. But every galaxy group, including ours, traces its history back to similar starting conditions in the early universe. The general process that built the vine is the same general process that built the structure surrounding the Milky Way. Smaller galaxies merged into larger ones. Mass clumped under gravity. Gas flowed along filaments. Star formation rose and fell as the structure assembled itself. The differences between the vine's eventual descendant cluster and our own local group come down to scale and density. The vine occupied a particularly dense seed region in the early universe, which is why it grew so massive. The Milky Way's neighborhood occupied a less dense seed region, which is why it stayed modest. Studying the vine helps us understand the entire spectrum of cosmic environments. By seeing how the densest, most aggressive seed regions evolved, cosmologists get a baseline for comparison with the slower, gentler regions like ours. The same physical processes operate everywhere, but the rates and outcomes vary depending on local conditions. There is also a more direct connection. Some of the small galaxies we see around the Milky Way today are remnants of what was, billions of years ago, a busier environment. The Milky Way's history includes mergers with smaller galaxies, periods of more intense star formation, and slow accumulation of mass from its surroundings. The patterns we see in the vine, in compressed and accelerated form, mirror patterns that the Milky Way also went through, just at lower intensity and over a longer span of time. By studying the vine, we get to see the cosmic processes that shaped our own galaxy's early life, played out at full volume in a different region of the universe. It is a kind of indirect time travel. We cannot watch our own neighborhood's early history directly. The light from that history is long gone, but we can watch other neighborhoods at similar early stages and infer how our own region must have looked. This is one of the deeper reasons astronomers care about distant structures like the vine. They are not just curiosities, they are pages from the cosmic biography that includes our own galaxy. The Webb era is particularly powerful in this regard. By providing detailed views of so many early galaxies and structures, Webb is letting cosmologists assemble a comprehensive picture of how the variety of present-day cosmic environments came to be. Dense clusters, modest groups, isolated galaxies, deep voids. All of them have origin stories that Webb is helping to write. Our local group, the Milky Way, the Sun, the Earth, all of us, sit somewhere in that broader cosmic landscape. The story of how our particular corner of the universe formed is connected to the story of how every other corner formed. The vine is one chapter in a story that includes us. But the vine is still keeping a secret, something about its structure that the team has not yet fully explained. The team has mapped the vine in detail. They have counted its galaxies, measured its mass, modeled its dark matter halo, identified its quenched giants, predicted its eventual evolution. The vine is one of the best understood early protoclusters in the entire observational record. But there is still a question that has not been answered. Why this shape? Why a bow? Why a curve? Rather than the more common, more disorderly distribution that most early structures show. Most early universe structures look messy, loose collections of galaxies with no clear pattern. The cosmic web has filaments, but they tend to be irregular, branched, and tangled. A clean, sweeping bow shape, 30 million light-years long, is unusual. It is one of the things that made the vine stand out in the first place. The team has theories. The shape may reflect the underlying distribution of dark matter in this particular region of the early universe. A particularly elongated, well-organized dark matter ridge, formed by the specific pattern of initial density fluctuations in this part of the cosmic soup, would naturally produce a bow-shaped chain of galaxies along its length. Alternatively, the shape may reflect a particular alignment of multiple smaller dark matter halos that were already migrating toward each other when the galaxies inside them lit up. The bow could be a snapshot of this alignment, with the 4 subgroups marking the locations of the most massive contributing halos. A third possibility is that the bow shape is partly an artifact of viewing angle. A more complex 3-dimensional structure, seen from a particular perspective, might present itself as a clean curve when projected onto the 2 dimensions of the Webb image. This is harder to test directly, but it cannot be entirely ruled out. Distinguishing between these possibilities will require more data, detailed mapping of the vine's galaxies in 3 dimensions, more precise measurements of their motions, and improved modeling of the underlying dark matter distribution will all help. The team is working on these follow-up analyses now. There is also the question of why the vine has produced as many quenched giants as it has. 11 quenched galaxies is a striking concentration. Other early protoclusters of similar mass have not always produced as many. What is special about the vine's environment that allowed so many galaxies to quench so fast? Possible answers include the specific merger history of the vine, the particular timing of its assembly, or the specific properties of its dark matter halo. None of these answers has been fully nailed down yet. The vine is still actively being studied, with new analyses appearing regularly. These open questions are part of what makes the vine such a productive research target. It is not a closed case. It is an ongoing investigation, with multiple lines of inquiry being pursued in parallel. Each new analysis tightens the picture a little. Each new follow-up observation provides new constraints. The vine will likely keep generating new findings for years to come. For working astronomers, this is a desirable state of affairs. A clean, well-defined object that yields new science with each round of investigation. A target that justifies continued telescope time. A structure that ties together multiple research programs across multiple subfields of cosmology. For the rest of us, the takeaway is more philosophical. Even the best mapped objects in the deep universe still hold mysteries. The more carefully we look, the more questions we find. The vine is no exception. Its surface has been mapped, its depths are still being explored, and the next round of exploration is already on the horizon. The story of the cosmic vine is not over. It is just getting started. Webb itself will keep looking. The extended growth strip is one of the regions of sky that Webb returns to repeatedly. Each new pointing adds depth, sensitivity, and coverage. Future observations will pull out more vine members, refine the redshift measurements, sharpen the maps of star formation activity, and tighten the constraints on the dark matter halo. Other instruments will join the effort. The Nancy Grace Roman Space Telescope, expected to begin operations within the next few years, will be able to survey wider areas of sky at infrared wavelengths similar to Webb. Roman will be especially valuable for mapping the broader environment around the vine. Where Webb provides detailed views of the structure itself, Roman will reveal the surrounding cosmic neighborhood that is destined to fall into the vine over cosmic time. Ground-based telescopes will contribute as well. The extremely large telescope, currently under construction in Chile, will provide the largest collecting area of any optical and infrared telescope ever built. When it comes online, it will be able to produce detailed spectra of even the faintest vine members, locking down their properties with precision that current instruments cannot match. Together, these next-generation instruments will turn the vine into one of the most thoroughly studied objects in the universe. By the end of the decade, cosmologists may have a near-complete map of the structure, a precise inventory of its members, a detailed understanding of its dark matter, and a confident prediction of its future evolution. The vine is also driving theoretical work. Researchers are developing new simulations specifically designed to reproduce structures like the vine. These simulations include refined models of dark matter clumping in the early universe, more aggressive star formation efficiency in dense regions, and faster quenching pathways for massive galaxies. Each new simulation is tested against the vine and other Webb-discovered protoclusters to see how well it matches. The interplay between observation and theory, with the vine sitting at the center, is producing rapid progress. The standard cosmological model is being refined in real time. New parameters are being tested. New physical processes are being added or removed from the standard recipe. Within a few years, the model that emerges may look noticeably different from the one we had before Webb launched. The vine, in this sense, is a turning point, not a single discovery that changes everything overnight, but a key piece of evidence in an accumulating body of findings that is reshaping how we understand the early universe. Future textbooks will mention it. Future cosmology courses will use it as an example. The bow-shaped chain, 12 billion years away, will become a permanent feature of the scientific narrative about how the cosmos built itself. For us, listening to this story right now, the takeaway is something like awe. A telescope parked far from Earth, looking at a small patch of sky between the Big Dipper and the Herdsman, has revealed a structure too large to fit in any easy intuition, too organized to fit any simple model, too early to fit the older textbooks. A structure where two giant galaxies have already gone quiet, where 11 quenched members tell a story of fast and violent assembly, where a dark scaffold pulls the whole shape together, where another structure hangs in the background as a ghostly companion. The universe is bigger, busier, and more dynamic than we knew. Webb is showing us that the cosmic vine is one of its loudest messages, and the next message, when it arrives, may be louder still.